Hello guys, welcome to our YouTube channel once more. So today we are going to be looking at a problem in maths mechanics, which is on center of gravity, BGS MOLYKO maths department. So question number 2 in that tutorial. So the question, just a little diagram on the question. The question goes: the figure shows a uniform lamina ABCD consisting of a semicircle of radius 2 meters and an isosceles triangle of height 2 meters. A says show that the center of mass of the semicircle is 8m on 3 pi from the vertical AC and along the horizontal BD. B says find the distance of the center of mass of the lamina from the vertical AC. And the last part says the lamina is freely suspended from A and hangs in equilibrium. Find to the nearest degree and the angle AC makes with the vertical. Alright guys, so let's dive right into the solution. So show that the center of mass of the semicircle is 8m over 3 pi from the vertical AC and along the horizontal BD. So what we want to do is want to give that semicircular lamina a new radius A, just for convenience purposes. Alright, the question told us 2m, but we're going to call the radius A. Then we're going to head over to draw the diagram here. Now just notice the way I've rotated AC. AC was a vertical line, but now I've put it on the basement, and then BD is now the one that bisects this line AC at the point O. Now the very first thing we want to do is want to give this semicircular lamina an equation. So you need to find the equation of the semicircular lamina. There's no way you're proving this proof if you cannot find the equation of the semicircular lamina. So it's the same equation that defines the circle that goes through all of these points. So what we want to do is want to assume that this center here is at the point is at the origin O, such that the coordinate of A, the x coordinate of A would just be negative A, and the x coordinate of this point C here would just be positive A. Now what we are going to do is to get the equation of the circle is y minus the y coordinate of the center, all that squared, plus x minus the x coordinate of the center, all that squared, equals to the radius squared. We have assumed the radius to be a here, so we have a squared here. X minus the x coordinate of the center, all that squared. So we have this point 0, 0 to be the origin. It means that the equation of the circle is basically just y squared plus x squared equals a squared. Now we can go ahead and then define the x and y coordinates of a centroid of this particular geometrical figure. So what you have to do to get the x and y coordinates is that you have to do these particular integrals. But there's something interesting about these integrals. Now you see this integral from negative a to a of y dx below here, which is the same thing for the y coordinate of the centroid. Now it's not for every particular question that you have to do this integral. Well, the GCE last year, June 2021, required you to do this integral, but other questions like the Northwest Mock 2018 and some other GCE questions were not required to perform this integral, especially when they are dealing with semicircular laminas like this, where you can easily just get the area. So this integral actually means that you want to find the area of this semicircle. That's what this integral means. That's what we've written here. So, but you realize that the area of this semicircular lamina is just pi radius squared over 2. So it replaces all of this integral, because the geometrical significance of integration is that you're finding the area bounded by that curve to the x-axis between the lines x equals a and x equals b if you are integrating from a to b. So we already know the area of a semicircular lamina, so we don't have to integrate in this particular case. Half pi a squared. Now to get this other integral, because we want to get the x coordinate of the centroid, to get this integral xy with respect to x, you realize that you have two different parameters or variables x and y with respect to a particular integration parameter delta x. So what you have to do is you have to unify them. Now to unify this thing, you have to go back to this equation and then differentiate implicitly. But before then, I just need you to realize that from A all the way to C, there's a line that bisects this region. So if I'm integrating from negative A all the way to A, it's just the same as 2 times the integral from this 0 to A, because this guy bisects this region. So that's what I've written here, 2 times 0 to A, x, y. So in place of x, y, what I'm going to do, I differentiate this guy implicitly. So I have 2y dy dx plus 2x equals 0, because if I differentiate this a square, I basically have 0. So what I have to do is I just have to make x dx the subject, right? So if I make x dx the subject from this equation, you realize I have negative y dy. Now in place of x dx here in this integral, I'll be replacing it with negative y dy. So I'm going to come over here and I'm going to write negative y dy. But now the problem is I'm not going to have the same integration limits from 0 to a, because now the integration parameter has changed. So I have to change the limits too. Now to change these limits, I just have to come back here. Now to get the corresponding limits of y, because now we are integrating with respect to y, when x is 0, what is y? That's what we want to ask. So when x is 0, take this lower limit and put it here. X is 0, y is just a. Now that's why you have a here. To go to the upper limit, when x is a, what is y? Take this a and put it here, get the value of y, which is just 0. You put it here. So that those are our new integration limits. So we go ahead and then we integrate. Now I can basically remove this negative sign by interchanging integration limits. So instead of a to 0, I can basically take from 0 to a, and then this negative disappears. I still have my 2 out here. When I integrate y squared, I have y cubed over 3. So multiply by this to have 2 third y cubed over 3. So I have now from 0 to a. I put in my limits. I have 2 third a cubed. Now to get my x bar, since my x bar is the integral of this divided by the area, the integral of this is just 2 third a cubed. I divided by the area, I have 4a over 3 pi. But what is my a? Originally my a is the radius of the circle, and the question told me that the radius of the circle is 2m. So in place of a, I just put my 2m there. I have 8m over 3 pi, which is exactly the proof. But then if you really want to think about it, because this is not really what the question is asking you, it's just that the x coordinate and the y coordinate of the centroid of a semicircular lamina are equal, right? That's why you would have 8m over 3 pi and 8m over 3 pi for both of them. The question is actually asking you to get the coordinate of the centroid from the vertical AC. So from this AC all the way along this BD would rather be the y coordinate when we rotate like this. So I'll just go ahead and get the y coordinate. Now to get the y coordinate, you have to come back here and integrate first. So you'll be integrating half integral from negative a to a y squared respect to x. But our y squared, you can come here and make y squared the subject. So what is your y squared? It's basically just a squared minus x squared. So you don't have to integrate y squared. You have to replace y squared with a squared minus x squared. So if I put that here, I'll be integrating this. When I integrate a squared, I simply have a squared x with respect to x. If I'm integrating with respect to x. So if I integrate negative x squared, I have negative x cubed over 3. So we'll just go ahead and then substitute in our limits, right? Upper limit minus lower limit, and then we'll have 2a cubed over 3. Then we'll divide that by this. We'll have 4a over 3 pi, and again our a is 2m, so you replace that, you have 8m over 3 pi. You realize that both the x and y coordinates of the centroid 8m over 3 pi, so it's just the same. That is the proof. So we can move over to the next part of the question. Alright, so the next part of the question says that we should find the distance of the center of mass of the lamina from the vertical AC. Alright, so whenever they are asked to find a distance of center of mass, yeah, it's just a cliche. It's a bit of a cliche in mass mechanics, center of gravity. So what you have to do is you just have to draw a table with portions like this, portions, and then you have their area, the width, and then the distance from the respective axis where you're taking your moments through. So you have the portions here. You have the semicircular lamina, right? This semicircular portion, and then you have the isosceles triangle, and then you have the whole lamina A, B, C, D, A, which is what your interest is, where your interest is. So you have each of their areas. You have to divide each of their areas. The area of the semicircular lamina is just pi radius squared over 2, and then you have that. And then because the radius is 2m, right? So in place of this guy, you put 2m. You have 4m squared, and then half, you have 2 pi m squared. Then place of isosceles triangle, half base times height. The base here is 4m, and then the height here is 2m. So half base times height, you are basically at 4m squared. Then the width, you just have to assume a particular parameter omega to be the width per unit area, so that you can take each of these areas, you multiply by omega, and then you have the width produced. The only reason why we are doing this is because we realize that we are going to be taking moments to be able to get this distance, right? To get the center of mass, you actually have to take moments, the center of gravity. So you have to take moments, and taking moments, you would actually need to use their width, the width of the respective regions. All right, so that's what we're doing. So if you want to look at the distance from AC, so you have to also study their distances from AC, each of those regions, right? So this semicircular lamina, you study its distance from AC. So you look at this, our AC here. So you realize that this AC is at O, right? It's like this is our reference axis. So to the left of it is going to be a negative displacement. To the right of it is going to be a positive displacement. Remember that moment is basically the product of a force times its perpendicular distance from the line of action of the force all the way to the pivot, right? So if you don't want to talk about a pivot like we do in physics, in mass mechanics you are talking about a particular reference rotating axis, right? Axis of rotation. So our axis of rotation here is AC. So you realize that this displacement to the left will be a negative displacement. That's why we say distance from AC would just simply be negative 8m over 3 pi, which is the center of mass of this semicircular lamina we found in the previous part of the question. And then you come over to the isosceles triangle. This is an isosceles triangle, so the center of mass from this AC will be somewhere here, which is simply 1/3 this total height, right? So if you're looking for the center of gravity of this isosceles triangle from a particular axis through D here, it would rather be 2/3 the height. So but since you are looking at it from AC, it will simply be 1/3 this height. So you realize that we would have the height is 2m, 1/3 of 2m is simply 2m over 3. Then the distance from AC of our whole lamina will just be x. We don't know where that is. It could be here, it could be this way, we don't know, but obviously it's going to be this way, so it's going to be a negative answer, right, to the left of this line AC. So we go ahead and then we take our moment. So what we really want to do when we're taking moments is that once to get the moment of the whole figure, so you have this whole figure here, the moment of this whole figure, which is the width times the distance from the pivot, from its own center of gravity, sorry, will be equals to the sum of these individual moments produced by the individual regions, right? So these two regions sum up to give you the whole lamina. So you sum up their individual moments too, since it's a vector sum. So you basically have the moment of the whole lamina here equals to the moment of our isosceles triangle here, the width times the distance from AC, which is this, minus, we are taking minus because the displacement of this guy is negative, so that's why this, when you multiply the width and this guy, it gives you a negative moment. That's why we're having minus there. So if we make x bar the subject, this x bar the subject, you basically have to divide all through by this, and then you realize that our x bar is basically negative 0.26. So negative 0.26 means that it is to the left, like I suggested. So our x bar is 0.26 meters from AC towards B. That's what that really means. Now when you have found the center of gravity of the whole figure, that is what you were asked. You can do more interesting things there now, like finding a particular angle, any point. If I hang this thing here, any axis can make an angle with the vertical or the horizontal. You can find that. That's the final interesting puzzle for some center of gravity question. Okay, so the final part of the question says that the lamina is freely suspended from A and hangs in equilibrium. Find the nearest degree the angle AC makes with the vertical. Oh, this is interesting. This is interesting. All right, so we have our diagram here. Now this is our center of gravity of the whole lamina. This is the point G, 0.26, 2. So this 2 is basically the distance from A, right? So, or perhaps from C here, right? So that's the height. Now you realize that our point P here, we just want to call a point P here, and then that point, the coordinate of this point P, which is directly below A, will be 0.2. But this is not how this this figure is going to hang when you hinge it at A. So it's going to hang like this. So it's going to rotate such that the center of mass of this object is, or the whole lamina is directly below the point where you hinge it, such that it can no longer produce, there are no moments produced by that center of mass about that pivot. You understand now? That's why it has to, the equilibrium, like a spoon. If you try to hang a spoon on a string, it's going to rotate until the center of mass of that spoon directly aligns with that pivot, with that support. This is how this thing is going to hang. So, but we can still solve it like this conveniently, or we solve it like this anyhow, but we can solve it like this. I'm going to solve it like this so that you can easily follow, but this is how the system actually is. All right, so we'll solve it like this, and now you have to realize that tan alpha, we call this angle alpha, tan of that angle is simply going to be GP, this is our GP down here, over AP, right? This height here divided by this small distance, and then our alpha is of course tan inverse of that, so our alpha will just basically be, what is this GP? It's simply the distance from this AC, and that's what the center of gravity of the whole lamina, 0.26, and our AP is basically what, 2 meters. So you realize that our alpha will just be 7 degrees to the nearest degree. All right guys, so that is the end of the problem. I hope you enjoyed this center of gravity problem. If you have many more problems in center of gravity, leave comments in the comment section below, even referencing us to solve a particular passage question or a particular tutorial question that you don't understand. Leave your comment below so we can verify. Thank you so much for watching. Please like, subscribe, and share to your friends if you enjoyed the video. Thank you so much.